The software is using the metric system, and all the input fields will be supplied with data generally in metric units. But there is help available if you work with a different unit system. If you go to the Utilities tab, there are some conversion factors that you can employ for the water flow rate, temperatures. Sometimes the pressure is given at an altitude and it will calculate the pressure for you to convert between meters and feet and inches, and also energy from BTUs per hour to watt. This other tab under the Utilities tab is the Merkle number calculator. If I click on that, I can supply it with inputs. Now with the cooling tower, the outlet water temperature is not known if you've got the inlet water temperature, but this tab is helping you to calculate the Merkle number if the outlet water temperature is already available, or if you want to design to that specific number. So if you've got a cooling tower that you need to design, you can enter all the values in here, the input and output values, and it can calculate the Merkle number that you need, and you can specify the fill or determine the fill that you need according to this total Merkle number. So you can also select to calculate the counterflow Merkle number according to the Merkle approach, counterflow according to the Popper approach, according to the ENTU approach, and then the same for cross-flow cooling towers. So if I click on Run, it will use all of these inputs, use the Chebyshev method to calculate the Merkle number according to the Merkle approach. For the Popper approach, it will use a very rigorous solution algorithm, and the ENTU method is relatively simple. The values for cross-flow takes a lot longer to calculate because it's a two-dimensional problem. The cross-flow Merkle number calculation according to the Merkle approach gives two graphs as output. It's the water temperature through the two-dimensional cooling tower. You can see it enters at a constant temperature, and as it flows through the cooling tower, falling down, it gets cooled by the air entering from the left. You can see that the water in contact with the inlet air cools down a bit quicker than that further in the cooling tower, and on the right hand side we see the enthalpy of the air as it moves through the cooling tower, entering at 100% and then increase to 150 all the way to more than 350 to the top part of the cooling tower, the air that is constantly in contact with the hot inlet water. The results for the Popper method takes even longer to calculate than the Merkle method because it's a much more rigorous method and it doesn't make the simplifying assumptions that is made in the Merkle method. It is solving across a two-dimensional space, a 20 by 20 grid. The 20 by 20 we've defined under the inputs, and here again you can see the water temperature field. Here we've got the air temperature field because it's specifically calculated by the Popper method, entering at 10 degrees, and as it flows through the cooling tower it heats up. The air that is in contact with the inlet water all the time heats up a lot quicker than the air at the bottom of the cooling tower. We've got the mass flow rate of the water entering at 100% at the top, and as the water evaporates you can see that the values decrease, and this is the saturation. So it enters the cooling tower at almost 84 and becomes saturated relatively quickly where the humidity ratio reaches 100%, and the air that's in contact with the water reach saturation relatively quickly, and according to this there will be an outlet plume because the air is super saturated with water vapor. The Merkle number calculator tab can also be used for very basic cooling tower sizing calculations. So if we enter all the inputs of the water and the air, so let's say the water inlet temperature is 40 degrees we require water outlet temperature of 25, and we supply the water flow rate and the airflow rate, and we select the counterflow method for Merkel. Now we can estimate the fill area, but it will use the fill that you've specified on the transfer areas. Now you can ignore the figure here, it will only access the fill type that you've selected. So let's, for argument's sake, said we selected the fill type 65, which is the Brentwood VF19 plus fill. If we go to the utilities tab, we have a we want to estimate the fill area needed, and we've also got a preferred water mass velocity, and a typical value there is like 4 kilograms per second per square meter. We also assume that in a cooling tower there will be 30% more transfer that will happen due to this rain zone and the spray zone. And if we say run, after we have selected estimate fill area, it will give us the Merkel number that it calculated from these values, and then it will go look at the fill and then calculate the dimensions of the fill necessary to get to the preferred water mass velocity, given the airflow rate here and the water flow rate here, and it estimates the following: that the full frontal area of the fill needs to be 31 square meters. That is a 5.6 by 5.6 meter cooling tower and a fill depth of 1.78 meters. If it's a natural draft cooling tower, that is just the diameter of the tower, which is 6.3, and the air mass velocity is 3.2. And we can play around with these values if we want to see what will happen if our preferred water mass velocity is 6. We can say 6, we can run it again, and we can see now the size of the cooling tower is less. The breadth and the width is 4.56. So this can be used as a very basic cooling tower sizing calculation.